Hi everyone, welcome to this presentation. My name is Yuan Wu. I'm a PhD student at Carleton University. Today, I will present our work, Mixup regularized adversarial networks for multi-domain text classification, which has been accepted by ICASSP2021. In traditional supervised machine learning, we aim to learn a function which maps the instance X to its corresponding label Y. Based on the types of the output, machine learning can be divided into three types. The first one is the regression, whose output is a scalar. The second one is the classification, whose output is a one-hot vector. And the third one is the structure learning, whose output is a sequence or a matrix. The structure learning contains tasks like machine translation and chatbot. Here, we show examples of machine translation and chatbot. The supervised machine learning algorithms need to improve their performance at some tasks with experiences. In particular, we use training samples to develop a function that can transform from the input space to the label space. Our goal is to find the best function which minimizes the error rates between the predictions and the ground truth labels. To date, machine learning has obtained remarkable achievements in various tasks, like computer vision, natural language processing, and speech recognition. These achievements are highly dependent on large amounts of labeled training data. Text classification is a fundamental task in natural language processing. Its input is a sentence and its output is a sentiment, which is generally a binary opposition in opinions. For example, when the input is "The story of the movie is boring and a waste of time," its corresponding sentiment is negative. With the advent of deep learning, text classification models yield impressive performance. However, there are still two issues for text classification models. The first one is that collecting sufficient text data for the target domain is often expensive and time-consuming. The second one is that text classification is a highly domain-dependent task. The same word in different domains may express different sentiments. For example, the word "easy" in the sentence, "This air conditioner is easy to use," expresses positive polarity, while in the sentence, "The ending of this movie is easy to guess," it presents negative polarity. Generally, when we need to handle scenarios where the training and test data distributions are different, we often utilize transfer learning techniques. In transfer learning, the differences between the training and test domains may lie in the feature spaces, the feature distributions, or the label spaces. Transfer learning can learn knowledge from one domain and generalize to another domain. Multi-domain text classification is a subfield of transfer learning. It's proposed to boost the average classification accuracy on multiple domains by leveraging available resources, including labeled and unlabeled text data among domains. Currently, the most recent MDTC approaches often adopt adversarial training and shared private paradigm. Adversarial training is first proposed by generative adversarial networks for image generation. It plays a two-player minimax game between the discriminator and the generator. The discriminator aims to distinguish generated images from the real images, while the generator tries to fool the discriminator. When these two components reach equilibrium, The distribution of the generated images can be regarded as similar as that of the real images. Then, adversarial training is extended to extract domain invariant features from the source and target domains for domain adaptation. The domain adversarial neural network employed adversarial training to perform alignment between the source and target feature distributions to generate domain invariant features. The domain invariant features can be regarded as both transferable and discriminative. The shared private paradigm, which is shown in Part B of Figure 3, consists of two types of feature extractor: the shared feature extractor and the domain-specific feature extractor. The domain separation network demonstrated that the domain-specific knowledge is beneficial to the classification of its own domain. Even though the adversarial training-based MDTC methods can yield state-of-the-art performance, they still face two challenges. The first one is that the existing MDTC methods often align marginal feature distributions by using adversarial training. However, successful global alignment may not guarantee successful class-wise local alignment, resulting in weak discriminability of the learned features. The second one is that, as we always use mini-batch stochastic gradient descent for optimization, if the batch size is small, samples drawn from multiple domains may not be sufficient to guarantee strong domain invariance of the shared latent space. Here in Figure 4, we show the mismatch risk when aligning marginal feature distributions in MDTC. The blue regions denote the distribution of the D1, and the yellow regions denote the distribution of D2. Part A shows the scenario before performing alignment. Part B shows the case when aligning the marginal feature distributions. A mismatch may occur with regard to the label. In order to alleviate the aforementioned two issues, we propose the mix-up regularized adversarial networks. Our work is inspired by mix-up. So first, we introduce mix-up. Mix-up is a data augmentation technique which constructs virtual samples with combinations of a pair of samples and their corresponding labels. It can encourage linear interpolation regularization in between training instances and address issues like memorization of corrupted labels and instability of adversarial training. Figure 5 illustrates the process of mix-up. Our work assumes that there exist M domains. Each domain contains two parts, a limited amount of labeled data and large amounts of unlabeled data. The MRAN model trains a domain discriminator, a classifier, a shared feature extractor, and a set of domain-specific feature extractors. First, in order to implement the standard adversarial training, we add the cross-entropy loss on the labeled data and the adversarial loss on both labeled and unlabeled data to our training algorithm. Then, we conduct the category and domain mix-up regularizations in the input space. For the category mix-up regularization, we first apply mix-up on the labeled samples in each domain to enforce prediction consistency. For the unlabeled samples, since we have no direct access to the label information, we use pseudo-labels in lieu of real labels. Here, we introduce a penalty that punishes the difference between the prediction of interpolations of two instances and the interpolation of predictions of these two instances. For the domain mix-up regularization, we conduct mix-up interpolation per domain, as the domain label of the instances sampled from one domain should be identical. It is not necessary to generate their pseudo-domain labels. The formulation of the domain mix-up regularization is defined as follows. Figure 6 shows the architecture of the proposed MRAN model. We conduct extensive experiments on two MDTC benchmarks, the Amazon review dataset and the FDU-MTL dataset. From Table 1 and Table 2, we can observe that the proposed MRAN method can outperform the baselines by 1.98% and 0.4% respectively. In addition, we conduct an ablation study on the Amazon review dataset. Here, we generate 4 variants of MRAN to explore the contributions of the labeled mix-up regularization term, unlabeled mix-up regularization term, and domain mix-up regularization term. From Table 3, we can see that all these 3 components can contribute to our MRAN model. In summary, we propose mix-up regularized adversarial networks for multi-domain text classification. The proposed MRAN introduces the category mix-up regularization to enforce consistent predictions in between training instances, imposing stronger discriminability to the learned features, and the domain mix-up regularization to explore more internal feature patterns in the shared latent space, leading to a more continuous shared latent space. These two mix-up-based interpolation regularizations can enhance and complement each other. The experiments on two MDTC benchmarks show that our MRAN method can effectively improve system performance. Thank you very much for your interest to our work.